Welcome back to the Foundry by Forge College. First off, a massive congratulations to you for crushing your previous course, the Capstone Mining Strategy Report. You spent all this time analyzing how to effectively mine blocks, secure the network, and process transactions. But listen, what if I told you there was a massive, foundational crack in the very structure of those transactions you've been working so hard to mine? I mean, early developers were practically tearing their hair out trying to build advanced features because of this one bug. And the terrifying part? It wasn't actually a flaw in the cryptography itself, it was just a quirk in how the data was packaged. So in today's explainer, we're going to dive right into exactly what that bug was, why fixing it was absolutely crucial if we ever wanted this technology to scale, and how an incredibly elegant engineering upgrade finally saved the day.
To really grasp the sheer panic this bug caused behind the scenes, I want you to picture something for a second. Imagine you write a physical check to someone. You carefully fill out the amount, the date, the recipient, and you sign it. Now imagine a mischievous middleman grabs that check before it gets to the bank. They take a slightly thicker pen and just trace right over your existing signature. They don't change the name, they don't change the money amount, they literally just make the ink a bit bolder. It's technically still your valid signature, right? A human bank teller would look at it and clear it without a second thought. But what if that thicker ink changes the overall shape just enough that it totally breaks the bank's automated scanning system? Suddenly, the computer throws a massive error. It thinks it's looking at a completely new, unrecognized piece of paper, even though the economic intent, moving your money, hasn't changed one single bit. Well, early smart contracts on the network were exactly that rigid. If the tracking number of a transaction changed unexpectedly, those contracts would just panic and fail. And that is exactly what was happening under the hood. So here's our engineering blueprint for today to understand how the network fixed this massive headache. We'll be looking at 1. The malleability problem. 2. Separating witness data. 3. Boosting throughput with weight. And 4. The soft fork strategy.
All right, Section 1, the malleability problem. Let's officially meet the villain of our story.
The core of this bug is something called transaction malleability. In plain English, it's the ability to alter a transaction's canonical identifier, what engineers call the txid, without actually changing the economic intent of the transfer. Before SegWit came along, the digital signatures that proved you had the authorization to spend your funds, they lived right inside the serialized transaction data. And because of the quirky ways cryptography and scripts interact, a random relay node on the network could subtly tweak the encoding of your signature as it passed it along. Now, to be clear, they absolutely could not steal your funds or change the destination. The math protected all of that. But this slight encoding change would completely alter the resulting transaction ID. This was an absolute nightmare if you were trying to build higher-level Layer 2 protocols like the Lightning Network. Those advanced networks rely on chaining together unconfirmed transaction IDs to route payments instantly. So if a random node on the base layer maliciously tweaks the ID of your anchor transaction while it's waiting to be confirmed, boom! The entire Layer 2 chain of smart contracts built on top of it instantly collapses. It is literally like trying to build a skyscraper on a foundation of quicksand.
Let's actually walk through the logic of how a transaction is processed so you can see just how fragile this is. Step 1. You serialize the core fields, meaning you package up the data about the sender, the receiver, and the amount into a neat digital format. Step 2. You add the witness signatures, which is your mathematical proof of ownership. Step 3. You take all that packaged data and run it through a double-shot 256 hashing algorithm to generate your unique transaction ID. And Step 4? Well, Step 4 is where it all falls apart. In cryptography, there's a concept known as the avalanche effect. If you change even a single tiny bit of data going into a hash function, the resulting output is wildly completely different. So simply hashing a transaction with two slightly different but totally valid signature encodings produces two entirely different 64-character transaction IDs. The core data, who gets the money, stayed exactly the same, but the final tracking number looked like an alien language. This proved just how incredibly fragile off-chain references were, and developers quickly realized there was no way they could build the future of decentralized finance on top of shifting IDs.
Moving on to Section 2, separating witness data. We found the bug. We know why the old system was failing. Now let's look at the brilliant aha moment that finally solved it. The solution is famously known as Segregated Witness. And honestly, the name tells you exactly what it does on a technical level. Under the pre-SegWit rules, signatures lived completely inside the serialized transaction bundle, which caused those malleable, fragile txids we just talked about. Post-SegWit, engineers introduced a new rule where signatures live in a completely separate witness area, creating perfectly stable txids. Think of it like this. Your transaction data is your wallet, and your signature is your ID card.
Under the old system, you basically had to staple your ID card to the outside of your wallet. If someone swapped your ID for a slightly thicker piece of plastic, the total weight and dimension of the whole package changed. Segregated witness literally segregates, or separates, the witness data, your ID card, and just puts it in a different pocket. It doesn't change who you are or how much money you have, it just keeps the accounting so much cleaner. By pulling the signature out of the data bundle used to calculate the hash, it suddenly doesn't matter if someone traces over your signature with a thicker pen. The txid remains immutable, rock solid, and perfectly stable. Identity and authorization were finally treated as two fundamentally different things.
Section 3. Boosting throughput with weight. Now, fixing that bug was absolutely vital for network stability. But as it turns out, this elegant little fix actually unlocked a massive hidden superpower for the network's overall capacity.
To fully appreciate this, we have to talk about a brand new concept the developers introduced called block weight. For years, the network had a super rigid, hard-coded limit. A block could only be exactly 1 megabyte in size. And let me tell you, trying to change that 1 megabyte rule would have required a massive, highly political network overhaul that absolutely nobody wanted to touch. So instead, engineers came up with a ridiculously clever accounting trick. They decided to split the data into two categories. The first category is the non-witness bytes. That's the core transaction data showing who sent what to whom. These are considered heavy and retain their full, original mathematical weight. The second category is the separated witness bytes, our signatures. These are treated as light and are heavily discounted in the new block weight calculation. It's essentially like dealing with a bouncer at an exclusive club with a strict maximum capacity. The developers tricked the legacy system by telling that 1 megabyte bouncer that the signature data is lightweight, so the bouncer happily lets way more data through the door without technically violating the old fire code limits.
But you might be wondering, why give witness bytes a discount in the first place? It's not just some blind loophole. The core engineering observation here is that witness data is essentially a validate once utility. Once a network node verifies that the cryptography is sound and the signature matches, it never really needs to mathematically check that specific signature again. Actually, some nodes can even prune or securely throw away that bulky signature data later on just to save hard drive space. Because this data is way less burdensome long-term, the discount makes total sense. And this is a game changer for the network's decentralization because it allows individual node operators to run the software on much cheaper consumer-grade hardware. By discounting the witness data, the network can cram way more transaction capacity into every single block. We get massive effective throughput growth without ever having to rewrite that dangerous hard-coded 1 megabyte legacy limit. It's a total win-win. A faster network, cheaper nodes, and all the strict safety rules remain perfectly intact.
Okay, Section 4, the soft fork strategy. So this all sounds incredible, right? You fix a massive structural bug, and you get a huge transaction capacity boost basically for free. But how on earth do you actually deploy a massive change like this to a global, decentralized network without splitting the entire community in two?
The answer was an absolute masterclass in decentralized coordination, the soft fork. A soft fork is an elegant, strictly backward-compatible upgrade. Its entire purpose is to minimize network disruption and actively prevent those disastrous accidental chain splits, where users get stranded on different versions of the software. How does it pull off this magic trick? By relying on the simple fact that older unupgraded nodes will still happily accept these new blocks without realizing anything has even changed. You can kind of think of the old nodes like oblivious grandparents observing a crazy new technological trend. To an old node, a SegWit block just looks like a block full of slightly weird but perfectly valid transactions. They just nod along and say, "Yep, looks fine to me," totally unaware of the massive architectural shift happening right under their noses. Meanwhile, the new, upgraded nodes see the separated witness data and strictly enforce all the new security semantics. It was a pragmatic, highly conservative compromise. It allowed the network to evolve safely, giving ample time for the entire global ecosystem of wallets, exchanges, and developers to adopt the new rules completely at their own pace.
Which brings us to our final, overarching thought for today. Identity is independent of authorization. Ultimately, SegWit proves that separating a transaction's identity, what the transfer fundamentally is, from its authorization, the cryptographic proof of who is actually allowed to send it, well, it isn't just a neat trick for good accounting. It is the absolute, non-negotiable foundation for all future Layer 2 scaling on the network. Without this fix, advanced protocols like the Lightning Network would have simply shattered under the weight of transaction malleability. I really hope this explainer has illuminated the sheer, brilliant engineering behind Segregated Witness for you. To dive deeper into the exact transaction structure, study the underlying code, and master other fascinating Web3 topics, make sure you head over to forge.college and explore everything the platform has to offer. But right before you go, I want you to ask yourself a question.
If simply separating identity from authorization unlocked this much hidden potential in throughput, what other massive bottlenecks are currently suffocating decentralized networks, just waiting for their own aha moment? Thanks for learning with us here at Forge College, and I will catch you in the next Explain.